Okay. We now have all of our groups set for the group presentations, and everybody knows who's in group 1, and everybody knows who's in group 2, and group 3 are those who are not in groups 1 and 2. So I'll make sure that everybody knows the groups, and I'll post them on Moodle as well. But here is just a quick reading. Group 1, the first presentation will be Daniel, Connor, Gabby, and Amelia. Group 2 will be Alwyn, Hannah, Max, and Russell. And group 3 will be Chione and Yari, Latifah, and Jessica. Basically tables. So those are the groups. Make sure that you get together with them, at least a week before your presentation so you can plan your presentation. And once again, you'll get a better grade on it and you'll help everybody more if it's something that's interesting and not just, and then we have this, and then we have this, and then we have this. Because that's my job. So getting on with the lecture today, we're going to talk about times and seasons, which sounds very much like a study in, Daniel and Revelation or something. Why do you suppose this picture here is the background that the textbook chose for this topic? Everybody recognizes that, right? Right. Stonehenge is believed, and there's really good reason to believe, that it was a calendar of sorts. On the winter solstice, the sun sets directly over this rock that was found out in front. They call it Pilot Rock, I think, and then shines through a window. And so it clearly was set up to align with the sun. I mean, that doesn't happen by just random chance. So that's why this is shown. It's an example of really ancient cultures. We know nothing about those Celts that made this. There are lots of competing theories about what they were doing and what was going on. But we can be pretty sure that it had astronomy as one of the basic things. I put this in here just because it's really funny to me. Let's look at this comment here. Richard Branson, the guy from Virgin Airlines and everything. Sunrise on Mars, quite an amazing photo. And then the comment, first one, what is it? Which is kind of silly, right? The second one, I never knew Mars had a sun. Yeah, that is a face palm there. The sun of Mars, coincidentally enough, is the same sun that we have because it's also part of the solar system. And here is, now I swear, I think that this is not a true photograph. Those don't look right for looking at objects, but it could be right because if you're on Mars, the atmosphere of Mars is about 1/100th as thick as our atmosphere. And our atmosphere is why stars twinkle and don't look like nice, pretty dots. So that could be realistic, right? If we had no atmosphere, we would never have stars twinkle. Because we have an atmosphere, we have regions that are warmer, regions that are colder. And as the light goes from a warmer region to a cooler region, it bends. And so the light bends as it goes through these different regions, and that causes where we see the stars to shift around a little bit, and that's why they look, twinkly and not as clear. And we'll learn in this when we learn about telescopes that scientists have actually developed a way to make adaptive optics to make their mirror on a telescope so the mirror modifies itself to stabilize the image and make the stars appear like they're not moving. And that allows them to get much clearer images. So if you were on Mars, you have Deimos and Phobos. Do you remember those from last night when we were looking at the size of things? The fear and terror. Those are the two moons of Mars, bright in the sky. Then we have Earth and Venus. Which one's closer to Mars, Earth or Venus? This is a bad question in case anybody realizes it and saying, I don't know how to answer. The question was, which is closer to Mars, Earth or Venus? If they were aligned together, it would be Earth. But the reason it's a bad question is if you don't know their alignment. Earth could be, close to the far side on the opposite side of the sun, which, that would be much farther away than Venus. You look at this picture, Venus looks brighter, so I suspect that since Earth and Venus are about the same size, but Earth is about 7% larger, I expect that the Earth must be significantly farther away, so it's somewhere, more distant on its orbit rather than a line close to Mars. By the way, since this seems to come up every year, I haven't seen it yet this year, Mars will never look the size of the moon in the sky. Never, ever, ever. Okay? Have you guys seen that on Facebook? On this day, it's usually like, August 23 or something. If you go out and look at Mars, it'll be the largest it ever looks, and it'll be as big as the moon. You guys ever seen that? No? Well, that's good. Most of you have missed out on the bad science. It actually started with good science. It was like August 23, 2003, when Earth was at its, what we call aphelion, the farthest distance it gets from the sun in its orbit. And Mars was at what we call the perihelion, the closest it gets to the sun in its orbit. And Mars was at opposition to, as viewed by the Earth, which means looking at the Earth, the sun was there and Mars was directly opposite. If you follow all of that geometry, what it meant was on that day, exaggerating, so let's say here's the sun, there's the orbit of Earth, and then the orbit of Mars is something like, excellent, that's not the tool I expected to choose. Still learning. The orbit of Mars was something like this, and so we were in a position like this where they were as close as they could ever get. But as close as it could ever get, Mars still looks like a speck in the sky. With your binoculars, you could tell that it is more than a speck, that it has some size to it. Never going to be confused with looking as big as the moon. People just made up stuff. And then made up pictures. This is what it's going to look like with a big old Mars and a little bit smaller moon. It was totally false. So it's good that you guys didn't see it, but if you ever see it, just know that ain't right. And then we have Rigel. Anybody know what Rigel is? It's the front foot of Orion. It's a star. It's a blue star. It's hot. And I believe Canopus is another star, but that's one I don't know. So these are, just looking at the sky on Mars without its atmosphere, it's kind of a cool picture. And keep in mind, Mars does have a sun. Nobody knows. The celestial sphere we talked about last night. I introduced a lot of things, and some of them we're going to talk about today in more detail. One of them is the celestial sphere. So the idea of the celestial sphere is a model to make it easier for us to find the locations of stars. We map out the stars just like we map out places on the Earth. The Earth is a sphere. We map out the places on the Earth. And because the stars are so far away from Earth, even though the stars are moving really quickly, they're so far away that the angle that they make per year, the angle it moves per year is measured by us, is essentially zero. So when we look at it, it looks like all the stars are staying fixed relative to each other and that the whole sky is rotating around. Now what's really happening? We're rotating around and the stars are just really far away. I like to think about this. I know you guys, not all from California, right? But I go to California, I like to go to Yosemite. You go up to Glacier Point. And at Glacier Point, you can look down Yosemite Valley and you see this big panoramic view. And the cars are going down there. And when I was a little kid, 7 years old, I'm looking at the cars, and the cars are just going so slow. And I was wondering, why are the cars going so slow? Are they looky-loos, looking at a bear or something? It wasn't until I got older, wiser, for the way my child was thinking, that I realized, no, the cars weren't going that slow. But, a car moving at 40 miles an hour, when you're looking at it from, 10 miles away, it doesn't appear to move very much in a second. And that's what's going on here, except that they're much, much, much farther away. So the model is, let's pretend that all of the stars are in fixed positions, and we make this spherical shell, and we just mark on the spherical shell the position where each of those stars appears on the spherical shell. We're inside that shell, and we look out, and it looks like all the stars are just fixed on the shelf. That's what the celestial sphere is. It's a model. Is it true? No. Stars are not on that spherical shelf. Is it useful? Yes. It's really useful because it allows us to make a map where we can find things. And so that's what this celestial sphere is. It's a way to map where the stars are. Now, the next slide is one that I picked up. I know that it's not original with the webpage I took it from, so I did give attribution to the wrong webpage. Besides that, I can't read Korean. But that celestial sphere, if we treat the celestial sphere model as if it's real, we on Earth are stationary and it's rotating around us. And so if you point somewhere and you just keep your hand pointing like this and you don't pay attention, where you're pointing to on that celestial sphere is going to change because it's rotating around you. And so at any time you look, they appear to move. Now, what's really happened? What? Okay, everything's moving, but what caused that motion was our motion. Right? We're the ones that are doing the rotation. As far as we're concerned, that celestial sphere is stationary. And we're rotating is the accurate story. And sometimes you'll hear me make a mistake and actually say, so the celestial sphere is rotating around us, just the sun goes around us. That's not correct. But, we tend to think of these things in funny ways. The motion then of that celestial sphere, the motion the stars make, is called the daily motion. Why daily? Because they go all the way around in one day as viewed from Earth. Actually, we do run rotation a day. Or the diurnal motion. And so one thing you can do is take these pretty pictures. I thought that was a pretty picture. How does somebody take a picture like that? Let me turn off more light so it stands out a little better. How does somebody take a picture like that? Have you ever wondered? It's kind of dark outside too. How do they do it? Okay, time-lapse photograph. If you look there, it says that this person took it on December 19, 2009 for 300 minutes. So the person just set their camera up on a tripod, opened the shutter, waited 5 hours, and closed the shutter. And this is what they captured in 5 hours. So what's making those circular arcs? Stars. They're stars. They're stars moving in the sky. Now, really what's rotating? The Earth. And so if you're on the Earth and the Earth is rotating, what part of the Earth isn't actually changing position? As the Earth rotates, what part doesn't change positions? The poles. So the poles will be stationary. So as you rotate around, the pole appears stationary, and stars directly above the pole will likewise appear stationary. Because with the celestial sphere model, which is very effective, we treat it like we're just inside here stationary, and there's a shell around us that's spinning. But the stars on the axes aren't going to move. And so you look there, and you can find the location that doesn't move. And that has to be what we call the north celestial pole. It's the place on the celestial sphere directly above the North Pole. But of course, what is directly above the North Pole of the celestial sphere? Polaris. So that means Polaris should be right at the center. Now, if you look at this picture, I'll even zoom in. The center should actually be somewhere around there. So you can see that Polaris is not at the center. It's off just a little bit. It's not a perfect pole star. It's offset a little bit from the pole. And of course, as was mentioned last night by Aldwin, the Earth is actually precessing. So Polaris has not always been the pole star. And in 13,000 years, Polaris will be about 47 degrees away from the celestial pole. But right now, it's very close. And if you look at these, the angle, change color here. The angle made by each star during this exposure, it doesn't matter how far away the star is, okay, I can't tell actually where that one begins. I think it's here. There was a second one underneath it that's basically the same place. All of those angles have to be the same because it's my wife back there. Because it's the angle the Earth rotates through in 300 minutes. So this photograph is made possible because we have that diurnal motion, the daily motion of the Earth rotating. And if you look at the stars, it appears like the stars are rotating. And I think these are very cool. I hope you do too. Otherwise, I turned on exactly the wrong lights. Those two. Now, some nomenclature, some points on that celestial sphere. Okay, I talked about the celestial North Pole. There's also, of course, the celestial South Pole. So we have the celestial poles that go straight up and straight down from the Earth's North and South Pole. We also have the celestial equator, which is just, we have the equator, which is halfway between the poles on Earth. Well, you boom, put that out onto the celestial sphere, and you have the celestial equator. But there's another thing that is easy to confuse with the celestial equator, and that's the line. It's shown on the picture, but not described on this one. I think it's on the next one. It's called the ecliptic. So we have a line. I'm pretty sure it's going to be in red ink on the next slide, so I'll put it in red ink on this one. The ecliptic. The ecliptic is the path that's shown here in turquoise. That's the path that the Earth sees the sun appear to go on as it goes through the stars. So if you look, where is the sun in the night sky? Of course, the sun's not in the night sky. That seems like a ridiculous question. But you know that the stars are out there. And so if you know where the stars are, you can figure out where the sun is. And so where's the sun in the sky as you observe it throughout the year? And the ecliptic is the path that the sun appears to take through the sky. And that ecliptic is not the same as the equator. Why? Because the Earth is tilted 23.5 degrees. So because the Earth is tilted 23.5 degrees, that means that the celestial equator, shown here in magenta, is tilted 23.5 degrees from the ecliptic. And the time when these cross, those are special times. We call them equinoxes, when the ecliptic crosses the equator. So what happens at an equinox? Well, the sun is over the equator is the basic answer. And we use that as a demarcation. The equinox will next come. We will have an equinox on, it's always around September 22. That's my mom's birthday. That's how I remember these things. And what's going to happen when we have the equinox? We will start fall. We start our seasons on two important things. The equinoxes, which is when the ecliptic crosses the celestial equator, and the solstices. The solstices are when the sun is the highest it gets in the northern hemisphere or the lowest it gets in the southern hemisphere. So on this picture, the solstices would actually turn out to be at this point and at that point for the solstices. And so we will have the winter solstice approximately December 22, and that's when we start winter. The summer solstice approximately, June 22? That's when we start the summer. So we start our seasons at these points of when the sun is the highest it gets, when it crosses the equator, and the lowest it gets. And there'll be more slides on that. Since obviously ecliptic wasn't here, I'm going to have slides coming up that has all the stuff I just said. Other terms. You see that Zenith, not just a brand of television. You guys probably don't know Zenith is a brand of television, do you? But you probably have seen some kinds of things. I think it was the last American brand of television. But Zenith has a meaning. And Zenith is the point directly overhead. So, Kind of like I say, wherever you go, there you are. Well, wherever you go, the zenith is straight above you. And so that's something that's dependent on the person. Where you are, your zenith is here. The opposite of the zenith is the nadir. The nadir is the point directly under your feet. So those are simple terms to help us identify places. Horizon, imagine this. If you were to make a horizontal plane, you would be pointing at the horizon. Once again, it's specific to where you are. So these are some terms we use with the celestial sphere to help us understand where things are located. Okay, now with the clickers, I think I mentioned last night, I am using them, but I won't be counting it toward grades this week because of I need to learn some stuff too. It should be, if you're using an actual physical clicker, channel 33. If you're using a smartphone, it should be session ID web ASTR. No space, a capital W and capital ASTR. So please, if you have a smartphone or clicker, because I want you to get practice and I want me to get practice, go ahead and answer. Everything should be open for you to answer. Okay. I got nothing. Actually, I didn't update my list before class, so that could also be a problem. All right, I got nothing, so I'm just going to move on you. I'm going to have you raise your hands instead. In which category does the celestial, or not raise your hands, blurt it out. In which category does the celestial sphere fall? Is it a fact, a hypothesis, a theory, a model, a law, or a principle? What? A model. She is correct. Thank you, Yari. A model isn't a fact. It's not true. We don't think that's how nature works. But it's an analogy that makes it easy for us to visualize and talk about something. And that's what the celestial sphere is. We know the stars aren't on this sphere going around the earth, but it makes it easy for us to use. When you go out and look at the night sky, you see these pretty, pretty pictures in the sky, right? I don't really see pictures there. Now, if you have just the right conditions, it's easier. But people have looked at these and said, I think I see something cool. So in this lower one, I pointed this one out last night. This is Deneb, which is the butt of the swan. And we can draw here what looks like a cross, but that's not all of it. That's just the cross. That's what we call an asterism. There's a constellation that's identified with this. You see it over here if you can read the word Cygnus. And you see this star here? That's also part of the wing of the swan. The wing of the swan doesn't end at the cross pieces of the cross. So its wing comes out like this, and there's a star there for the wing. If you look here, you can actually see, and then its wing is supposed to come back like this. And you have the area. I'm trying to match the picture here as best I can. I usually just draw these with mostly straight lines. Something like that is the area that is identified as the constellation. So you look in there, it has constellation, and once you see, the stick figure to kind of make out the swan, then when you look at the sky, you can see it. But the first who came up, it had to be kind of imaginative. I had some students, about a decade ago, who for their presentation, they gave us a star map and had us just make up our own constellations. And I found the Lombardi Trophy. It's one of those great constellations that the Raiders have found 3 different times. They lost it twice, but that's beside the point. So that is one constellation which you should easily identify after we've gone out to lab a few times. Now, this upper one is one that's not generally in the sky during our labs since we're going out in the fall. But to me, when I look at this, what I see reminds me of the Sphinx, which is cool because it's actually supposed to be a lion. If you look over in this picture, it's got, some other things going on. I don't know exactly how it is. It'll be on the next slide. But you've got a lion here, something like that, and I don't know what's going on with its head. Here's a picture superimposed over it. Looks exactly like that, right? No, it doesn't. That's a picture there to kind of guide you. Now, this bottom one, the Cygnus the Swan, one of the things that cracks me up is I have software on my phone, StarWalk, that has pictures of the constellations. They have the swan flying the other direction. I'm like, how do you make that mistake? I mean, it's got the long neck, right? Long neck, short to the butt, not long to the butt and short to the head. But, they're just putting pictures to it. So let's talk about those constellations. I told you last night there are 88 constellations. How much of the sky do these 88 constellations cover? All of it. Right. Every single piece of the sky is in a constellation. And constellation boundaries are kind of just randomly chosen to include as much of the pictogram of this one, as much of the pictogram of this one that goes with them. And so stars are often named with that Bayer naming convention, alpha, beta, whatever, and the constellation. Asterisms are not constellations. Asterisms are just star pictures that aren't necessarily within one constellation and aren't the pictogram that goes with the constellation. So, for instance, with that cross was not the pictogram of the swan. If it was the pictogram of the swan, it wouldn't count. So asterisms, they're loosely defined. You can make up an asterism and just start calling that and hope that the rest of the world adopts it. Right? They're not actually officially recorded. So, my Lombardi constellation, I could have started calling that an asterism and tried to make it popular with my friends. Who knows, could have come up with something. So some popular patterns, some popular asterisms are the Big Dipper. And then I have here the Teapot, part of Sagittarius. Now, in lab, the first couple labs, we're going to spend time pointing out Sagittarius very specifically. The reason is, now Sagittarius won't be there when you do your lab final. So you won't be able to use what we're teaching you there in the lab final, which is fine. We try to teach lots of things in classes that we don't test over. Sagittarius is an important thing. It's not on this picture, and I don't think it's on the next one either. Nope. But it's an important thing because the center of the Milky Way galaxy has been identified to be in the constellation Sagittarius. In fact, that teapot, it's a figure that looks like that. And so you connect the dot picture. Looks like that, right? That's the teapot, short and stout. Actually, no, I forgot. There's two more stars out here. There's the handle. There's the spout. It gets all steamed up, in case you know the song. Well, why is this important as far as the Milky Way galaxy? Because the center of the Milky Way galaxy is right out here. So it kind of looks like, you're pouring the milk out, and that's where the center of the Milky Way galaxy is. And so we're going to be very specific in pointing out where that is so you can find it. So if it's in the sky, you can say, oh, the center of the Milky Way galaxy is over there. Right. So it's a good thing to know if you're actually into astronomy where the center is. Now, the constellations that we're going to focus on mostly, aside from those two, we're going to focus on constellations that fit into the name circumpolar. Now, we know circumnavigate, like, Columbus set up to circumnavigate the globe. Or circumference. Circumpolar means they go around the pole. And the term circumpolar specifically means that these constellations will always be above your horizon. That means if it's dark out, you'll be able to see them. Obviously, it depends on where you are, what the circumpolar constellations are. We are about 4 degrees north of the equator. Since we're about 40 degrees north of the equator, that means that, anything that's from the North Pole up to 50 degrees, 40 plus 50 is 90, will always be visible in the night sky. So for us, circumpolar constellations are constellations that are within 50 degrees of the North Celestial Pole. And so we'll focus on those because it doesn't matter what time of year you go out. If it's nighttime, you'll be able to see those circumpolar constellations. Other constellations will rise and set throughout the year. There are some constellations that we'll never get a chance to see. Ones that are more than 50 degrees south. Is 50? Yeah. Ones that are more than 50 degrees south of the equator, we never get to see in the northern hemisphere. And so obviously we won't look at those because they're not visible. I was excited a few years back when I went to Malaysia to be able to do things like view the Southern Cross that we never get to see in the northern hemisphere. I know, I get excited about random things. I was excited for at least 2 minutes. So everybody got that word circumpolar? Yeah, a lot of words today. An interesting thing to think about. Where does the sun rise? Where does the sun set? Is it really that dark out? There must be nobody having classes because the lights are out in the hall. When you watch the stars rise, first of all, where do the stars rise? In the east. Where does the sun rise? In the east. How many people have watched the TV show Street Smarts? It's actually a really funny show. The premise of the show is, it's kind of like Jimmy Kimmel TV stuff. They go out and they find people on the streets and they ask them random questions. And they try to find 3 idiots. And they ask them the set of questions and then they come to the game show and you see the 3 people and we ask them this question and you have different rounds like how many got it right, or which one got it right, and that kind of thing. And so one of theirs was, how many people got it right? And the question went like this. In the northern hemisphere, the sun rises in the east and sets in the west. In the southern hemisphere, where does the sun rise? So pretend you're on the game show. You got money riding on this. Of these 3 idiots, it's really sad to say these 3 idiots, but it wouldn't be a fun game show if everybody just knew all the answers. Of these 3 people, how many do you suppose knew where the sun rose in the southern hemisphere? Okay, Max says 1. Hannah's going all kinds of optimistic, 0. Anyone more optimistic than these 2? I should have prefaced it by they're all idiots. Yeah, it turned out Max is right. 1 person got correct where the sun rises in the southern hemisphere. So now let me ask you, put me on the spot. This is where having clickers would be good because it's completely anonymous, but then you have to set up a quick question and know what you're doing. Where do you think the sun rises if you're in the southern hemisphere? I know nobody wants me to say they're idiots and then say, oh, you got it wrong, you're an idiot. You're not idiots, none of you, okay? Everybody down with that? Even if you get the question wrong. Well, why does the sun in the northern hemisphere rise in the east? What's happening to make stars rise? The Earth is rotating. The Earth is rotating, so we are constantly heading east. And so we see things come up in the east and set in the west because we're heading east. So if you're in the southern hemisphere, what direction are we rotating? East, so where are things going to rise? East, right? Doesn't matter where you are, it's the Earth's rotation that makes them rise in the east and set in the west. But east and west is a relative term. The sun does not always rise on the equator in the east. It does not always set on the equator in the west. It depends on where you are and what time of year. So in this picture, first of all, would you declare those stars rising or setting? Setting, because there's an arrow pointing toward the horizon. Very astute. Okay, so we have the stars setting. They're not going straight down. They're going at an angle. Why would they be at an angle? Yeah, the Earth is tilted. The Earth is tilted 23.5 degrees. And so as it rotates, the stars are going like this. And if you're in the northern hemisphere, they're going to appear to go north when they set. And so that's why they're appearing to go north and west rather than just go west. And so you can actually, observe where the sun rises in the morning. The sun, since we're we're 40 degrees north, and the sun can only go between 23.5 north of the equator and 23.5 south of the equator because of our tip, right? 23.5 degrees between the eclipse and the equator. The sun at noon is always going to be south of us. Now, what identifies noon? Here's what it's not. It's not your watch.
It's when the sun is at the highest point.
It's when the sun is at the highest point. We have a term to help us identify that. We talked about your zenith. That's pointing straight up. We also can talk about your meridian. Now, you guys know things like the prime meridian, which goes from the North Pole to the South Pole through Greenwich. What? Through Greenwich? Yeah, so the International Date Line is 180 degrees for that. Well, your meridian goes from the North Pole through your zenith to the South Pole. And so when the sun crosses your meridian, it's local noon. That's how we define local noon. Our times on our watches don't match local noon. Sometimes the real noon might be at 1:30. It's not at noon. I should point out some other things. AM versus PM. What does AM mean? The words. Anybody know the words? I'm going to write these down. AM is anti-meridian, not anti, anti. We've heard terms like antebellum. Same anti, not the same as if you're playing poker. Actually, it probably is the same as when you're playing poker. Because when do you ante up in poker? Before they deal. Ante means before. So AM, anti-meridian, means before meridian. It's before the sun is on your meridian. So in the AM, in the anti-meridian, is before the sun has reached the meridian. PM, what does PM stand for? Post-meridian. And of course, I did not check the spelling of meridian, so if there's supposed to be a double letter somewhere that I missed, sue me. You won't get your money for suing me. So post-meridian is when the sun is past the meridian. That means the middle point, which we call noon. Is noon technically AM or PM? Another bad question, by the way. It's neither. It's on the meridian at noon. It's not before, it's not after, it's on the meridian. So you don't have a 12 AM or a 12 PM. You have 12 noon or the opposite, 12 midnight, when it's on. I don't know a name for the line that goes from the north to south going through your nadir. Okay, I spent more time on this than planned. That's okay. We've got 10 more minutes and 20 more slides. Only have to do 2 a minute. All right, on Earth, we know our place by latitudes and longitudes. I had a teacher try to tell me longitude are long. And I was like, but the latitude lines never end. And anyway, latitudes are the lines that tell us how far north or south we are. So they're circles going around the globe that are parallel to the equator. Longitude go from pole to pole and tell us how far around the Earth we are. So we measure our latitudes and longitudes. The latitude is measured from the equator, either north or south, and the longitude is measured from that prime meridian, either east or west. So that's how we get our coordinates. In this day and age, everybody's down with their GPS, giving them coordinates for their latitude and longitude. That's how we can navigate on Earth and how our phone can tell us where we are and where we need to go. And by the way, if anybody cares, my brother and sister were born about there. I, on the other hand, was born about there. What was that? Can't see them? Are you?
Oh, there they are.
Yeah. Anyway, I like it because, it has there the hump of Africa where we lived is visible. So that's how we do things on Earth. In the sky, we essentially do the same thing, but we have different words. So on Earth, we had latitude. In the sky, instead of latitude, we have declination. So latitude was measured north or south of the equator on the Earth. In the sky, the declination is exactly the same. It's north or south of the celestial equator. So since I am approximately 40 degrees north of latitude, that means my zenith, the point straight above me, is at 40 degrees north declination. Question, Russell? What was that?
There's one in the east and the west.
The declinations are these lines here, which are telling you how far north or south. Do I have? Yeah, they're running east-west.
Okay.
They're running like this. And so that tells you how far north or south. They're at a constant amount north or south. Now, the complement to the latitude was the longitude. And for astronomy on the celestial sphere, we use what we call the right ascension. Now, the right ascension is a little more convoluted term. Declination, you can think about, decline. Okay, I can see you're going up or down, north or south. What ascends in the sky? Just a question to help us get the meaning in our head.
In the morning.
In the morning, the sun will ascend in the sky. Okay, what we're measuring with the right ascension is how the sky ascends and on the other side descends. So it's measuring the equivalent of the longitude, and as the Earth rotates, what's above my head will always be declination of 40 degrees north, but the right ascension will be changing because of the rotation of the Earth. And in fact, go ahead.
Is our angle constant, or does it change?
Our
tail comes in.
Our declination, our latitude and longitude, this location, this building is going to stay the same latitude and longitude essentially forever because there's virtually no plate motion here. They say that we're on a craton, which is a non-moving piece of the Earth's crust. So here, we're going to have the same. Now, if you were to go somewhere like, let's say Skagway, Alaska, you might be moving an inch a year or so. Nobody's going to consider that a change, but technically it is. And I don't think that's what you meant. So our latitude and longitude we can consider fixed for a given location. You put a marker in the ground, it's going to have the same latitude and longitude. The only changes that we'll get there is if somebody comes up with a better surveying method and they're more accurate. Then when we go to the sky, because the Earth is rotating about this axis and the sky, as far as we're concerned, is stationary, then that means since we stay at the same latitude, we stay at the same declination at all times. But because of the rotation, our right ascension is continually changing. And it's changing with the clock, because the clock is based on the Earth's rotation. And so how many hours are in a day?
24, 20 something.
Yeah. 24 is the number we give. It's 24 hours from average mean solar days, 24 hours. That means the average time continues means 24 hours. Question next.
So the grid, the way it's drawn is fixed, but because the Earth moves, which changes our east-west rotation. So the grid is fixed, but when the Earth moves, it changes our east-west
Yeah.
rotation.
So-
on the grid.
Yeah, so you're stationary one place on the Earth, but this whole grid is rotating like this past you.
Okay.
Right, that is in the sky. On Earth, you're staying in the same place in the grid, but the sky is rotating with respect to that.
Oh, in the celestial sphere.
Yeah.
Okay.
And so the right ascension, we actually use units of hours, minutes, and seconds to measure it, because then you can say, what's overhead right now is at 12 hours right ascension. And so 1 hour later, it's going to be 13 hours right ascension because it's just been 1 hour later. And so it's easy to map how the right ascension changes because it changes with your clock. You can use your clock to measure how much the right ascension changes. So right ascension is measured in hours, minutes, and seconds instead of degrees. So that's a unique thing to think about. And that's where it's not 24 hours because the actual time for one rotation is slightly less. Now, I'm clearly not going to get through today's lecture. I'm just a slow teacher. Why do you suppose that the mean day, that is the time from noon to noon, is 24 hours, but the time for one rotation is slightly less? Okay, what makes a day going from noon to noon? What makes the day? Noon to noon requires us to do what?
Rotate.
We have to rotate, but it's not just one rotation. Noon is when the sun is overhead, but the Earth is orbiting around the sun. So we might start here, and as I start moving, okay, so I'm going to start here, so I'm facing right at the projector, and the projector is going to be the sun. So I start moving and I start rotating, and I come over here, and now I've done exactly one rotation. Am I facing the projector? No, why not? Because I have rotated around. So I'm going to have to keep going and go a little further in my rotation. So now I've done one rotation plus this amount before I get to noon again. So it's actually more than one complete rotation to go from noon to noon. In fact, if I went around the table and you counted how many full rotations I had and how many times I faced the projector, you'd find that in one complete cycle, which for us would be one complete year, I would face the projector, face the sun, one less time than the number of rotations I did. And so the relationship between the number of rotations in a year and the number of days in a year is that there is one more rotation in a year than there are days in a year. So there's 365.2422 days in a year, thus there's 366.2422 rotations in a year. And taking that ratio, you can instantly calculate how long the time is for one rotation. This is just an example of a map showing right ascensions and declinations. So this here is a line of declination. As we talked about earlier, it's running east-west. This is 40 degrees north, wherever you are in that line of declination. And then we have the lines of right ascension that are marked in hour increments, 1 hour, 2 hours, 0 hours. 0 hours must be the equivalent to the prime meridian. That's the place that we are referencing from. That's one of the things in lab we're going to have to point out. It's called the equinoctial couleur. So you're going to be able to locate that in lab, and it's not that hard. And if you look at this picture, we have Andromeda and Perseus, it says. And look at this picture. It's hard to figure out even where Andromeda is. Oh, yeah. Okay, this is Perseus above and Andromeda below. Perseus, where's Pegasus? Well, I'm not going to waste my time trying to figure it out right now because I didn't look at it before. When you're looking at things in the sky, the distance between things is determined by angle. Right? You can't put a meter stick up there and say, oh, the moon is this many centimeters away from, Rigel. Right? That's meaningless. If you hold it closer, you're going to get a different number. If you hold it farther away, you're going to get a different number. So what we can do is measure the angles. And just things to make it easy, our rules of thumb. That picture on the right The hand is very dark. But that's supposed to be a hand. I'll turn the lights back off so you can see the hand. And the hand here is just as a general reference based on typical human sizes of hands, arms. If you put your hand out in front of you at arm's length, spread it out, the distance from pinky to thumb should be about 20 degrees across the sky. Now, if you have freakishly large or small hands, it's going to vary. It's a rough number. The width of your thumb should be about 2 degrees, the width of your pinky about 1 degree. So there are things that you can use to try to gauge the angular separations between things in the sky. And there's another picture like that. I'm out of time. I'm going to end by talking about this, though, because it's truly cool. The analemma. Have you guys seen pictures like this of the analemma? These are pictures where throughout the year, like every 10 days or so, you take a picture from exactly the same location at noon or at the same time of day. So you take a picture periodically throughout the entire year at the same location at the same time. But the position of the sun moves. The position of the sun moves for a couple reasons. One, of course, is that we're tilted as we go around the sun. We're going to see it at different angles. But the other one is we actually travel faster when we're closer to the sun, slower when we're farther away from the sun. And so that causes the Earth's rotation to vary with time, and the time that we are in, the seasons to vary. And so that's why this is not symmetric. It's a combination of a couple of effects. Okay, got to go. I'll see you Friday.